To practice using our TI calculators, I will be making some videos or working in class with you to go over how to use them. To begin, we're going to plug in this function into our calculator, and we want to graph it and give a window that gives us a full picture of the graph. We wouldn't want a window that only shows a tiny piece. We would want to adjust the window on our calculator settings in order to get a full picture of the graph. So you'll turn on your calculator, and to enter an equation to graph it, we press the y equals button up in this top left corner, and then we will plug in negative, remember to use the negative symbol, not the minus, 0.2 x. Any variable is used, this button is used to cover any variable, x cubed, so use caret to get into the exponent, and then a 3. You'll need to use the right arrow to get out of that exponent, minus 2.2 x squared plus 1.6 x plus 1. To graph it, we'll press the graph button in the top right corner. It's loading. Now, this looks kind of like a parabola. So, do we have the full picture? Maybe so, except this is not a parabola. It's a cubic function. And I know from experience that cubic functions usually are some sort of a wave. So that's what I think this might be. It might be some part of a wave. To begin with a better window, I feel like it's really below, we're really looking at the lower half. So I'm going to press window. The minimum x value that I really want to expand the x-axis because I'm only getting some part of it. So maybe I'll do negative 25 to positive 25. And then I want to see more of the negative part of the y-axis because I want to see more below. So I'm going to say negative 25. But then I also noticed that the y, I don't need to see much above there. So I'm going to say about 5 for the y-axis. You have to graph and test if that is a good window. We have a pretty good picture here, but I think we could shave off some from the x-axis and then give us a little bit more of the lower y-axis. So from our window, we're going to go negative, let's take off 10, so we'll go to negative 15, and the x's, the positive x's, don't need to go too far, so maybe 5. We still have a ways to go, so let's try negative 55, and then my y maximum, I'll keep it. So we'll go ahead and graph that. So we have a pretty good picture. On the x-axis, we're going from negative 15 to 5. On the y-axis, we're going from negative 55 to 5. Negative 15 to 5 is my interval for the x-axis. Now I know what I'm really looking for when I'm drawing. The scale that we're using is 1 unit. The next question is asking us to find the zeros for this function, the same one. There's actually a function on your calculator to find zeros. You're going to press second trace, which tells your calculator calculate. You can calculate this function at a certain value. You can find the zeros. You can find a minimum, a maximum, an intersection, derivative, or integral. So we're going to find the zeros, but the calculator is not just going to give you the zeros. You need to give the calculator a region, an estimated region where the zeros are. So I see zeros are my x-intercepts, or the x part of the x-intercept. So I want to be to the left of the x-intercept there. So right above, and then I'm going to move the little x to the right, which is right below in this case. And then once I have my left bound and my right bound of the region for which there is a 0, I press enter again, and the calculator has given me a 0. It says y equals 6 e negative 12. That's 6 times 10 to the negative 12. That's a really, 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 really small decimal. It's basically 0. So our 0 here is negative 11.64986. Negative 11.68946. In calculus, you will be rounding or truncating to 3 decimal places for the AP exam. And here we have one of the zeros. But it appears as though there are 3 zeros. To calculate another 0, we're going to do the same thing that we did before. If you don't want to push the arrow down, you can just select the number 2, and it knows that you wanted to find a 0. Enter for the left bound, enter for the right bound, and then enter again, negative 0.406. So a left bound could be here, a right bound could be here, and then we press enter. 1.056. Great. Those are the zeros of this function. Now we need to find the points of intersection for these two equations. Also, write the equation that you are solving. For points of intersection, we would use methods like graphing and look at the points of intersection literally, substitution, elimination. To show substitution, I'm going to just add this y on both sides and get it in y-intercept form, equals 3x plus 5. And then y is also equal to this cubic polynomial. So if y is equal to this and y is equal to this, then these two things are equal to each other. And that's the equation that we want to solve. Now, do you want to solve this equation? Might get a little complicated. So what we're going to do is we're going to graph these two equations, this one and this one, and then we're going to use the intersect tool on our calculators to find the points of intersection. I have plugged in my functions and now I'm going to graph them. Our window is crazy from the last problem. If you ever want to go back to just the standard window, you can press zoom, and then 6 would be standard. So 6, or you can scroll down to the 6. And now we're back to negative 10 to 10, negative 10 to 10 for both axes. This feels like a better picture, a clearer picture of what we're looking at here. But I do want to zoom in. I'm looking at those points of intersection, so I'm going to change the window just for my own convenience to negative 5 to 5 on the x-axis. Kind of zoom that in. And we didn't need to zoom in, but I like to do that. So to find the points of intersection, we will press second trace, again, telling the calculator to calculate. Number 5 is the intersection, so you can scroll down to 5 and then hit enter, or you can just hit 5 and that selects it. For an intersection, we are going to get our little x as close to that intersection as possible, and then we're going to press enter 3 times. Enter, enter, enter. When I rounded the y value, I got 862. Let's find that other intersection. So second trace is going to get me to calculate, and then I want to find an intersection, so I'm going to click 5. Get my little x as close to the actual point of intersection as possible. Press enter 3 times. Our intersection is listed here. These are my points of intersection. Use a calculator to solve the absolute value of x squared minus 5 greater than or equal to 4. Write your answer in both inequality notation and interval notation. We want to know for all the intervals that this function, the absolute value of x squared minus 5, so we'll call that y1, when is that greater than or equal to this function? 4. y2 is what we'll call that. That's just a constant. So what we're going to do is graph both of these and look for the intervals for which y1 is greater than or equal to y2. To plug these in, I will go to y equals, and then it is absolute value. So where do we get the absolute value symbols? We'll go to math, go to the right one to num, and then that's the first option, absolute value. So you press enter or the number 1. And we had x squared minus 5 and y2 is equal to 4. Now we're going to graph. Here's what our graph looks like, and I have sketched it to the left. We want to know all the intervals for which the blue graph is greater than the red graph. That would be to the left of this intersection point, right? The blue is above. In between these two intersections, and to the right of this intersection point. These are all the intervals for which the blue is greater than or equal to the red graph. We just need to know what are these x values, and that will give me the intervals. To find those points of intersection, I'm going to use the intersect tool, second, trace, 5, go to any intersection, hover the X over it, and press enter 3 times. The intersection here is -3, 4. Here I've drawn it as just the x's because we're not concerned with the y values for interval notation. We're going to find that other intersection point. We have 4 of them to find. That intersection is -1, 4. Again, we don't care about the y values, so -1. It looks like this graph is symmetric about the y-axis. If you remember how to test for that type of symmetry, you can see, or you can just continue to look for the other intersection points. I'm going to give you a hint, / the answer. It is symmetrical, so these are 1 and 3. The yellow intervals are my answer. So I'm going to write in inequality notation and in interval notation. Interval notation is what I'm more comfortable with, so it goes from -infinity all the way up to +infinity, just the yellow intervals. -infinity, -3, -1, 1 is the next interval, and 3, infinity. Now, we go back to the inequality symbol from the beginning, and that is when is it greater than or equal to. So we are allowed to include those points of intersection. So this would be bracket, 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 bracket. But infinity never has a bracket around it. It's always parentheses because you cannot include infinity. Infinity is just a concept or a direction. You are not required to put the union signs in between. Inequality notation would be anything less than or equal to -3. So x can be less than or equal to -3. X can also be greater than or equal to +3. And then that interval in between, the x is in the middle. You sandwich the least to greatest. For a compound inequality, the symbols are always opening to the right, and we have the or equal to because of our original inequality. These are the intervals for my answer.